Welcome to the second part of the third week of classes. Today we're going to talk about locks. In the previous segment we spoke about synchronization in general. Today we're going to focus on specifics of how to implement locks. So we're going to try to solve, we've already tried to solve the synchronization problem with the abstraction called locks. So today we'll take a look at its implementation, the performance considerations, the trade-offs, the design trade-offs. Okay, so how to implement locks. So to try to do that, the first thing we've got to understand is what is a lock, and so what are the semantics, what is its specific role or purpose in a program. So the purpose of a lock is to prevent a thread from doing something, to prevent another thread from doing something. That is its sole purpose. So if you have more than one person trying to acquire the lock at the same time, then it needs to ensure that only one person gets the lock and the rest of them don't. Okay, so this is the critical semantic of lock. So the general idea is that once you have this, then you can essentially implement a critical section by getting the lock before the critical section and unlocking it when you leave it. Furthermore, if you try to get the lock and someone else already has it, then you just simply wait. So you spin, or you can do other things. So you just keep spinning in a loop, periodically testing the lock to check if it's free. Or you can get out of the way and possibly even stop and wait. So there are a lot of different trade-offs as to how to even wait efficiently. Right? So if you have an busy loop, then you're wasting precious CPU time. Okay. So the general way in which a lock is implemented these days is we look at a few implementation choices and a couple of algorithms. But in general idea is that there is a hardware lock instruction. So this is a special instruction that the CPU gives you. And when you use this instruction, you can implement a lock using a specific variable. So you can, we look at how a lock is acquired and how you inform the other threads that you want to block from doing something. How do you inform them that they haven't got the lock? And in general, how you release the lock. Right? And all of these come with a specific instruction called a lock instruction. There are different styles of lock instructions based on how you want to indicate whether the lock is obtained or not. Like, are we going to use Boolean values, which is 1 or 0? Are we going to use other values? So on and so forth. The complexity of this, in general, it was done in 432. All processors included these days. It's not a question of complexity anymore. In the past, it used to be, not anymore. Most systems do include, and it's just considered as a bare bones requirement in order to help people do parallel programming. Another way of implementing a lock is putting a task to sleep. So we look at this implementation where how do you handle the interaction between the hardware and the scheduler itself? So can you implement a lock by just saying, can you prevent a task from doing something by just putting it to sleep? What happens if it gets the lock and then goes to sleep? Right? It could be pretty bad because you've got the lock. No one else could be doing anything else because they are waiting on the lock, and the scheduler puts you to sleep. So is there any interaction between the scheduler and the CPU scheduler and the hardware itself? That is, the thread which got the lock also is the thread that gets to run on the CPU. Okay. So the next thing we'll look at is an illustration of a lock-based mutual exclusion. So the rule is that only one thread can hold the lock at a time. So if you look in this case, first T0 holds it, then T1 holds it. So when T0 holds it, T1's waiting on it, then T1 gets it, T2's waiting on it, T3, and so on. So at any given instant, you notice that time flows top to down. So at any given instant, you notice that only one thread holds the lock. And if another thread tries to get the lock at the same time, for example, in this case, T1 is trying to get the lock as T0, same time as T0, then it just has to wait. right? So this essentially guarantees mutual exclusion, that T1 could not have the lock at the same time as T0. The performance implications of this is that lock contention, first of all, limits parallelism, right? So essentially, T1's not doing any useful work in this picture, the wait times, right, the white portions. Um, this is your performance implication, right? The overhead of the system. So this is the part that limits the parallelism. Okay, and then there's the general overhead for the lock, acquire, and release, right? So if you look at each point, when you get the lock, there's a small window where the application is not doing any useful work. So the point at which you get the lock and you release it, that adds overheads itself, right? So those are the things to watch out for. There are also correctness implications with locks, or using locks to implement mutual exclusion. And one example of this is a deadlock situation involving two locks, A and B, and we have two threads, T1 and T2. So what's going to happen is T1 holds lock A, tries to acquire B. T2 in the meantime holds lock B and tries to acquire it. This is a classical deadlock situation, right? Neither of them is going to be able to get the lock because T1 is going to be waiting on T2 to release B, and T2 is going to be waiting on T1 to release A. And so what's going to happen is you're just going to have circular wait. So T1, T2, and then T1 is waiting on B, and T2 is waiting on A, right? And so you have a loop, and so neither of them is going to be able to make progress, and so you have a bad situation, right? And this can happen when you start using locks. There are possible solutions to it. The solution, one widely used solution, is just acquire all the locks in the same order, right? So don't allow this. The problem is that T1 held A and then went for B, and T2 held B and then went for A. If you acquire them in the order, if you said that both threads have to acquire them in the order A followed by B, then this situation wouldn't happen. And this is called acquiring locks in order, right? So if you acquire locks in a global order, all threads do the same thing, then there's no chance of a deadlock, right? The way a lock instruction is implemented in hardware is using what's known as a read, modify, write instruction. So note that this is fundamentally different than a read or a write instruction. It's two things in one. So previously you only saw that you could either read or write a variable, right? But now there's this new operation called a read, modify, write. So it's two things rolled into one. So what is a read, modify, write? A read, modify, write is an atomic isolated operation, right? You read a memory variable into a register and you write a new value simultaneously into the same location. So you read a value and you write it, right, at the same time. Okay. In general, we look at the trade-offs as to why read, modify, write instructions are expensive in multi-core processors. Normally, there's also a comparison step. So it's not just reading and writing. You read it, you compare the value against a specific value that you expect in the variable, and then you would write back if that value exists. So there's also an equals operation. So an example of this, first example of this would be a test and set. Most systems provide this. You read a value from a memory, you check if the value is a 0, and if it's a 0, then you write back 1 to the location. Okay. If values, so if it's equals 0, then it's 1. If it's not equals 0, then whatever value there was in the system, you leave it as it is. Right. So that is what a test and set is. So you also have a more generic version that's called a compare and swap. So if you have a compare and swap, the subtle difference is that you read the value, you check if it's equal to some value v that you've provided, and if the value is v, then you write the new value. If the value is not v, then you just so if the value is not equal to v, then you just leave it as it is. Okay, so those are the two things that